Hi, welcome back. Let's get to our goal straight away. The goal of today's lecture is to characterize integral closures of Noetherian integrally closed domains over finite separable extensions. So there's a lot to unpack in this goal. So let's do it one by one. We'll recall what it means for something to be an integral closure. That's closely related to integrally closed domains. We'll also recall what it means for a ring to be Noetherian, and we'll also recall some properties of finite separable extensions that we'll need. Okay. So I'll just give a lot of reminders. So recall from the previous lecture, what was the setup? We had a domain which we called A, and then we took its field of fractions, so we call the fraction field K, and we had this notation OA, but the notation OA had an ambient field L, so it depended on this ambient field. So just to emphasize the ambient field, I'm also going to put the ambient field in the notation OAK. This is the set of elements of K that are integral over A. Okay, so this OAK was called the integral closure of A in K, and we say that A is integrally closed if, so A naturally sits inside OAK. We say that A is integrally closed if A equals OAK. Okay, so just a short lemma. So suppose you have a finite field extension L over K, and you take an element alpha in L, then there exists an element in K that's non-zero, there's an element, let's call it C. In A it's not 0, says that C times alpha is in fact integral over A. And what's the proof? Since L over K is finite, say of degree n, so then alpha must satisfy a monic polynomial of degree n with coefficients in K. Okay, but what we also have is that this field K is actually the fraction field of A. So each of these coefficients has a numerator and denominator, where the numerator and the denominator belong to A. So just by clearing the denominators, without loss of generality, I'll often abbreviate without loss of generality as WLOG. We may simply assume that alpha satisfies an equation of this form: a n alpha to the n plus a n minus 1 alpha to the n minus 1, and so on and so forth, a 1 alpha plus a naught equal to 0, where the coefficients a n minus 1, so on and so forth, a 1, a 0, these are in A. These equations are, because we cleared out denominators, this new equation is no longer monic. So this new equation is no longer monic. But remember the way we got this equation is we started with a monic polynomial of degree n with coefficients in k, and then we cleared denominators. So this leading term a n, another additional constraint is that this leading term a n is not 0. Okay, so we have a non-zero term, and if you just multiply throughout, by the n minus first power of a n, what do we get? We get a n to the n times alpha to the n plus a n minus 1, and now we can write this as a n to the n minus 1 times alpha to the n minus 1 plus so on and so forth, a 1 a n alpha a n to the n minus 2 plus a naught times a n to the n minus 1. Okay. Now if you just group things, if you just group the powers of a n and alpha, what do we get? We get a n alpha to the n plus a n minus 1 a n alpha to the n minus 1 plus so on and so forth, a 1 a n to the n minus 2 times a n alpha plus a naught a n to the n minus 1 equals 0. Okay. So we get that this term a n alpha, so we get a n alpha satisfies a monic equation, but if you observe all the coefficients a n minus 1 and so on and so forth, a 1 times this power of a n, all these coefficients, so these coefficients are in A. So a n alpha in fact satisfies a monic equation over A, and hence a n alpha is integral over A. And since a n is not 0, we can choose C to be a n. Okay. And this completes the proof of the lemma. Okay, and a rough tagline for this lemma is just that whenever you have an algebraic element, the tagline is if you clear denominators, you can clear denominators to get an integral element. Okay. Now I want to recall some facts from ring theory. I want to move on to this next tag, Noetherian rings. So some facts from ring theory which I'll just remind. So suppose you have a ring R, and suppose you have a module, an R module M. M is said to be a Noetherian R module if every R submodule n of M is a finitely generated R module. And just as in the previous lectures, I'll abbreviate finitely generated by f dot g dot. Okay, so module M is Noetherian if every submodule is finitely generated. So in particular, if M is a Noetherian R module, you can choose the submodule M itself, you get that M has to be finitely generated. So in particular, if M is a Noetherian R module, then M is a finitely generated R module. However, the converse doesn't always hold. However, in general, the converse needn't hold. A finitely generated R module M needn't be Noetherian. Now, however, if you have a Noetherian ring, so R is said to be a Noetherian ring if every ideal I of R is a finitely generated R module. So in other words, as a module over itself, R is finitely generated. So if you work with Noetherian rings, things are nice. So if R is a Noetherian ring, then it does turn out that if M is a finitely generated R module, then M is a Noetherian R module. So in particular, if R is a Noetherian ring and M is a finitely generated R module, then every R submodule N of M is also a finitely generated R module. Okay. So those were some reminders about Noetherian rings and finitely generated modules over Noetherian rings. The next reminder is from field and Galois theory. Again, so if you have a field extension, say L over K, so you have an inclusion of K into L, that turns L into a vector space over K. So we say that this field extension is finite if as a vector space over K, L is finite dimensional. So if the dimension of L as a vector space over K is finite. And so this dimension is often called the degree of this field extension. And it's also denoted by L:K in parentheses. Okay. And we say a finite field extension L over K is separable if for every element in L, you can look at its minimal polynomial over K, so if you look at its minimal polynomial, that has distinct roots. It has no repeated roots. So I'll mention some consequences, some results related to finite field separable extensions. So suppose L over K is a finite separable field extension, and often just to abbreviate I will just say finite and separable. And suppose alpha is an element of L, then via the multiplication by alpha map, so we get this map M alpha from L to L, and it has this property that this is actually a K linear transformation. So we can think of L as a vector space over K, so we can think of L as a vector space over K, and M alpha is a linear K linear transformation. And associated with linear transformation, there is this trace and determinant. So this trace of this element alpha is, you look at this corresponding linear transformation M alpha and you take the trace of that. The norm of this element alpha from L to K, you look at the linear transformation and you take its determinant. Okay, so here when I say trace and determinant, I'm considering the trace and determinant of the linear transformation, this K linear transformation M alpha. Okay, and maybe one observation, so the trace function itself gives you a map from L and actually lands in K, and in fact the trace function is K linear. That is, if you give me two elements alpha 1 and alpha 2 and I take its trace, that's the same as taking the trace of alpha 1 and taking the trace of alpha 2 separately and adding them up. for any two alpha 1 and alpha 2 in L. And if you give me an alpha in L and if you give me a scalar in K and you multiply them out, take the trace, that's the same thing as first taking the trace and then multiplying with the scalar. So for all C in K and alpha in L. Okay, so this was some sort of abstract description of the trace and norm as trace and determinant as trace and determinant of a K-linear transformation. In our case, the field extension L over K is finite separable, so there's an alternate description. So when L over K is finite separable, there is an alternate characterization or an alternate description of this trace map and the norm map. So our field extension is separable. So you consider sigma 1 to sigma n, let them denote the distinct field embeddings of L into its separable closure. And remember that since L over K is finite separable, the separable closure of L equals the separable closure of K. So we are looking at all the distinct field embeddings that fix K, and by fixing K we mean if what we mean is that sigma of x equals x for all x in K. Okay, and just some observations. Since L over K is finite separable, so the degree of the field extension is in fact equal to the cardinality of this distinct field embeddings of L into its separable closure that fix K. So the sigma 1 up to sigma n, that's what I call n. Okay. So all of these sigma i's are field embeddings of L into its separable closure. Okay, and one more observation. If you have an element in L with the property that all of these embeddings sigma I fix alpha, so if alpha belongs to L with sigma I of alpha equals alpha for all these embeddings I going from 1 to n, then that element should actually belong to K. Okay, so with these priors, so the trace of an element alpha is in fact the sum of its conjugates. So these sigma I alpha, these are called the conjugates of alpha, and the norm of an element is actually the product of its conjugates. Okay, and with this perspective, one can see that the trace of an element belongs to K and that the norm of an element also belongs to K. Okay, so let's move on to the next lemma. So suppose A is a domain with fraction field K. And suppose L over K is a finite separable extension. Suppose you have an element alpha in L that is integral over A. Then for every field embedding from L to its separable closure, which turns out to be the separable closure of K as well, what we have is that sigma of alpha is integral over A. So if you start with an integral element, its conjugate is also integral. So what's the proof? Since you have an integral element, since alpha is integral over A, we know that it satisfies a monic equation over A. So let's say it's alpha to the m plus am minus 1, alpha to the m minus 1, so on and so forth, where these coefficients belong to A. Now if we apply this field embedding of sigma into separable closure, so applying sigma, sorry, I should say that the field embedding fixing K, sorry, I forgot the hypothesis that the field embedding should fix K, and since the field embedding fixes K, we have that sigma of AI equals AI, since all these coefficients AI belong to A, which in fact sits inside K. If you apply sigma to alpha to the I, you get sigma of alpha to the I, and so what we get is sigma of alpha to the, once you apply sigma to this equation, we get a new monic equation over A satisfied by sigma of alpha, and then if you stare at it a little bit, you actually see that it's in fact the same monic equation. So we obtain that in fact sigma of alpha is integral over A, and this monic equation has the same coefficients am minus 1, am minus 2, so on and so forth, a1, a naught. So in fact it satisfies the same monic equation that alpha does. Okay. So we have an immediate corollary to this lemma. So suppose A is a domain with fraction field K, and suppose L over K is a finite separable extension, and suppose alpha in L is integral over A, Then we talked about taking the trace and norm. So the trace and norm are integral over A, and in particular, if A is integrally closed, then the trace and the norm in fact belong to A. Okay. So let's see a quick proof of this. So if you have an integral element and you take the trace and norm, those should also be integral. This is an immediate corollary of the previous lemma. So you take the field embeddings, the distinct field embeddings, sigma I from L into its separable closure, fixing K, by the previous lemma, each of the sigma alpha is integral over A and now just to introduce some notation, let OAL denote the set of elements of L that are integral over A, and let OAK denote the set of elements of K that are integral over A. And by proposition 2 from one of the earlier lectures, these sets are actually rings. And so if you take the trace of alpha, it's the sum of its conjugate sigma f alpha. So we've just shown that each sigma of alpha is integral, but if you add integral elements, you still get something integral. So the trace in fact belongs to OAL. And similarly, the norm of alpha from L to K is the product of all the conjugates sigma of alpha, but each conjugate sigma of alpha is integral over A, so its product should also be integral over A, so it belongs to OAL. But what we've seen is that, or let me say it this way, so these are, so both of them are integral over A, but they also belong to K. So just by how they defined, the trace and norm also belong to K. They are integral over A, so they must belong to the set of elements in K that are integral over A, which we denoted OAK. And so in particular, if A is integrally closed, which by definitions mean that A equals OAK, then the trace of alpha from L to K and the norm of alpha from L to K, both of them belong to A. Okay, so that concludes the corollary. So this completes the proof of the corollary. Okay, some more facts about finite separable extension. So if L over K is a finite separable extension, so we can consider the trace from L to K. And as we discussed earlier, this is a K-linear map. Moreover, the fact that I want to recall is that this map is non-degenerate. That is, there is an alpha, or let me call it alpha naught, that's non-zero, with the property that the trace of this element, which is the sum of its conjugates, is non-zero. Okay, so when you have a finite separable field extension, the trace function is non-degenerate, and what that means is that there exists an alpha naught with the property that its trace is non-zero. Okay, so this fact, so it's from Galois theory or field theory. And it uses linear independence of characters. That is, so you have these distinct field embeddings from L to its separable closure. It actually gives rise to a character from the multiplicative group of L to the multiplicative group of its separable closure. So, and what we have is that since these characters are distinct, they are linearly independent. Say over L. And this fact essentially allows you to show that the trace function is non-degenerate when you have a finite separable extension. Okay, I'll conclude by stating the main result that I wanted to say, which is our goal, and we'll prove that result in the next lecture. This is proposition 8. I'll give a statement. So let A be a Noetherian integrally closed domain let K denote its faction field, let L over K be a finite separable extension. And let B denote the set of elements of L that are integral over A. So we know from proposition 2 that this is a ring which contains A, so it in fact inherits an A module structure. The conclusion is that in this setup, B is in fact a finitely generated A module. Okay, so if your base ring A is Noetherian and integrally closed, then this integral closure B in L turns out to be a finitely generated A module. So to prove this proposition is our goal for the next lecture. Thank you.